By now we know how to find the derivative of the natural log of x, and that is 1 over x, the reciprocal function. But what if the log function that we're trying to find the derivative of is not the natural log, but it's the log of some other base? Maybe it's a common log of some sort, or a log that has a base that is not e, like log base 5 of x. So what I'd like to do in this video is show you how to find the derivatives of logs that aren't natural logs. And to begin, we'll look down here at letter D on this activity, where we have the function y equals log base 5 of x, and it says to write that function using natural logs. And to do that, we're going to use what's called the change of base formula. Now, the change of base formula allows me to rewrite any log function or expression in some base into another base by using division. And the way I like to remember change of base is I put the argument of the log in the attic, A for argument, A for attic, and then I put the base of that log in the basement, B for base, B for basement. So the attic of my fraction versus the basement of my fraction, the numerator versus the denominator. So if the argument x goes in the attic, then I have the natural log of x up there, and then I can put the natural log of 5 in the basement. And that's my equivalent expression for log base 5 of x. And let's get more clever here and rewrite this. This is really, I'm going to circle here the number 1 over ln 5. And I'm just going to be a little bit more creative with this, with the way that I write this. So 1 over natural log of 5 times the natural log of x is really what I wrote. And this 1 over ln 5 is a number. That's simply a constant. And the reason that's important is because when I now go to write the derivative of this expression, well, then f prime of x, a constant times a function, f prime of x is simply going to be the constant, that same constant, times the derivative of that function. And the derivative of my ln x is 1 over x. And from that, we can derive a formula where if I have the log of any base, right there I have a lowercase b for any base, here's my derivative. dy dx is simply this right here. I'm going to have 1 over, and I'll write the x in front here, 1 over x times the natural log of that base. So I still have my ln of the base down there in the denominator, and then this x represents the log argument from that original log expression. So there's our formula, a good one to memorize so that we can write derivatives of now any log function that we come across. So now some examples. Number 1 says to differentiate, the function is y equals log base 2 of 3x. So let's see here. I'm going to look at that 3x as the argument, and my formula for dy dx of logs says to go 1 over the argument times the natural log of the base, also in the denominator. Now don't forget the chain rule. Chain rule still applies here. So I need to multiply that by the derivative of the argument, which is a 3. Now the 3's are going to cancel here, so I'm going to end up with a simplified derivative of 1 over x times the natural log of 2. No plus c because we're not integrating, we're writing derivatives. Let's try number 2. Derivative will be 1 over, it's a log again, so 1 over the argument of the log times the natural log of the base, also in the denominator. Now the derivative of my sine function in the argument there is cosine. That's the chain rule step. And so now, cosine over sine I can simplify to cotangent. So there's a nice derivative for number 2. And then let's look ahead at number 3, where this is a little bit weird. I don't know that you would ever see this. I think if we wanted to look at the natural log, then the problem would actually have ln. But here it says log base e, but we should know that log base e is simply the natural log. So this is really 4 times the natural log of x to the power of 10. Don't forget about log properties. I can apply the power rule here, exponent swing, and rewrite that as y equals 10 times 4 times the natural log of x. That's the log of a power property. So use properties to make your calculus easier. So far, I've done nothing but just some simplifying steps right here, and now I'm ready to write the derivative of 40 times the natural log of x, which would just be 40 times 1 over x. Now, in conclusion, I'm going to skip down here to this problem here that says number 6, and there's a little asterisk here, and there's a clue. We're going to use another type of logarithmic differentiation to solve this problem right here. So number 6 actually involves logs, and we're going to use this logarithmic differentiation technique whenever you have a function raised to another function. So anything in the pattern of I have an f of x raised to the power of some other function like g of x, a function raised to a function. And when that happens, what I'd like to do here to simplify is I want to take the natural log of both sides of my equation. And then let's perform an exponent swing over here. So again, the log of a power can be written as that exponent written in front as a multiplier times natural log of x. And now what I have here is sine of x times natural log of x. I'm going to take the derivative of the entire equation implicitly with respect to x here. So the derivative of natural log of y is 1 over y, but I have to do a chain rule piece times dy dx. And then here it's going to be the product rule. So derivative of the first times the second plus the first times derivative of the second. There's the product rule from a few units ago. Now remember that we're trying to find the derivative of this expression here, y equals x to the power of sine x. So I'm looking for dy dx. And dy dx is right here. Let's isolate it. So to finish the problem here, I want to multiply by y to get rid of this y over here. So dy dx will equal y times all of this cosine x times the natural log of x plus the sine of x over x. And then maybe one final step here. We want to make sure that our derivative is written in terms of x. So rather than leaving a y right here, let's go back and substitute in x to the sine x, because that's what y equals. So final answer, dy dx equals x to the power of sine x, just substitution from the original problem, and then all of this, cosine x ln x plus the sine of x over x. That's called logarithmic differentiation, a strategy that helps us find the derivative if I have a power raised to another power. And that's what differentiating logs is all about.